For the start of this next chapter, we're going to cover the concept of formula mass. Also, you'll many times hear the term molar mass or molecular mass as well. These are related concepts. The idea behind a formula mass is it's related to the mass of the sum of all the average atomic masses of all the atoms in a particular formula. So, for example, you take the molecule CO2. And if you wanted to know the mass of an average molecule of CO2, it turns out it's about, and we'll look at how to calculate this as we go through this section, 16, 32, 44. So it is 44.01 grams per mole. That means if you have a mole of CO2, you would have 44.01 grams of CO2. This takes into account the fact that, for example, carbon has multiple isotopes that occur at different ratios. That's why we say it's the average atomic mass. Now, in the case of a covalent substance like CO2, it is a discrete molecule. So, like, it is carbon double bonded to two oxygens, each of them with a lone pair. So we'll also refer this to sometimes a term called molecular mass, or I'll use the term molar mass more often. So it's the mass of a mole of this particular compound. And it exists as a bunch of different CO2 units. The reason we care about this is this helps to do conversions later on in the course. The idea is it lets us convert between mass, which is something we're very good at measuring with a tool like a scale, or with something called gas laws that we'll go over later for the specific instances of gases, whereas moles are not as easy to calculate in some instances, so we can convert between them. I don't have a scale that tells me how many moles something is, but I know how many grams it is. I can then convert it to moles, as long as I know what the substance is. Now, here's an example from the text, figure 6.2. It takes the molecule CHCl3. So, this molecule has 3 chlorine atoms, 1 carbon atom, and 1 hydrogen atom. And the way we figure out the atomic mass is we get it for each component of the molecule. And so these numbers can all be found on your periodic table. So, for example, if you look up carbon, the average molar mass for carbon is 12.01 grams per mole. Or, back from the units we were using earlier, a single carbon atom has a mass of 12.01 AMUs. So, either one, you can look those up, and you do it for each atom. So there's 1 carbon, 1 hydrogen, and then 3 chlorines. So for the carbon and hydrogen, we just add those numbers to our total. But in the case of chlorine, we have to multiply it by 3. So we take 35.45 and multiply it by 3, and then we add all 3 numbers together, and we get a molecular mass, or molar mass, of 119.37. This means that there are 119.37 grams of CHCl3 per mole of CHCl3. And as a reminder, we can convert between the units AMUs and grams per mole, that both units will give us the same result, although they're intending different things. AMU is about the mass of a single molecule, grams per mole is about a large number of them. As a reminder of what this unit here means then, is we effectively know there are 119.37 grams of CHCl3 in 1 mole of CHCl3. And you'll see as we go throughout the class, the rest of them will use this as a conversion factor. So that means we can also write it as 119.37 grams of CHCl3 over 1 mole of CHCl3, which we can now use in dimensional analysis problems. Or we can also write that 1 mole of there we go, that's an H. I had a few too many letters there. Cl3 is 119.37 grams of CHCl3. And I realized my face, oh no, okay, there's a Cl behind my face. That got blocked off a tiny bit, but you know what's there. Both of these are equal to 1 because while they're in very different units, the quantities they represent are the same. This is why we can use these in dimensional analysis to convert between one unit and another, because we know that they are equivalents to each other. So this will be useful to us, and that's why we're going to use this number a lot. A second example from your text is the molecule C9H8O4, or aspirin. So again, we look up the atomic mass of each of them from the periodic table. These numbers come from that bottom part on your periodic table for each atom: carbon 12.01, hydrogen 1.008, oxygen 16. We then multiply by the number of each of these, and we get a total that we then add together. And so we now know that there are 180.15 grams of aspirin, C9H8O4, in 1 mole of aspirin. C9H8O4. That H should be a little bit smaller. It's supposed to be a subscript. And generally, you'll see it written as 180.15 grams per mole when you're asked what a molar mass of something is. You will also see it written in AMUs, and that's also true. Both those statements are true statements. The mass of a single molecule of this is 180.15 AMUs. The mass of a mole of this molecule is 180.15 grams. You will use the grams per mole more often because it's useful in conversions, but the AMU statement is also true. So you should be able to recognize both and be fine with that. Now, I'll mention something that is a distinction that is important conceptually, but just not to stress too much on it. You'll be able to solve problems okay. But the issue here is that ionic compounds are a bit different than covalent compounds. If you remember, we talked about it. Something like NaCl, for example. If you have sodium chloride, you don't just have one Na plus and one Cl minus. This sodium gets surrounded by chlorines, and those chlorines get surrounded by sodiums. And this goes on in really large networks that extend for huge distances. So there aren't single NAs and Cls we can say are paired together by themselves. This is different than the molecule carbon dioxide we talked about earlier. There are single molecules that are, this is one C and two O's, and these are the things that interact with each other. With an ionic compound, something like sodium chloride, you have large C's of these sodium and chloride ions. So they don't have we know they occur in a 1-to-1 ratio, but it's not that there are two distinct atoms that stick together and then the rest are separate. For this reason, technically in terms of naming, you wouldn't call it a molecular mass because it's not the mass of one molecule. You instead use the term formula mass. This is the reason you'll sometimes use different terms for what seems as a chemistry student at first to be the same idea. Because at the end of the day, we will use them similarly. They're giving us the same information. How does the mass compare to the number of these molecules present? It's just their form is a little different. So behind the scenes, if you think about it conceptually, they're a little different. So we would actually use different terms for them. And so that's why you'll sometimes see those terms, formula mass versus molar mass. Note that you could also talk about the formula mass of CO2. That's okay. It's just that technically NaCl, I wouldn't think of it as being a molecular mass. But none of the rest of the problem solving changes. So for example, in our sodium chloride example, the ratio is 1-to-1. It's always 1 Na to 1 Cl. So you look up the values of each. Na is 22.99, Cl is 35.44. There's one of each of them, so you just multiply by 1. When you add it together, you get that there are 58.44 grams of NaCl per 1 mole of NaCl. So 58.44 grams per mole. Which also means that a single, if you only had one sodium ion and one chloride ion, it would have a mass of 58.44 AMUs. So we can still use this as a similar conversion. We can convert between moles and grams and moles. So those same ideas with molecular masses apply here to when I technically can only say it's a formula mass. So in terms of solving questions, your problem-solving skills do not change at all for using this information. Now, let me go over one more thing of how this could be useful then. So we did conversions back during the molecule chapter, during the chapter on atoms, where you convert between grams and moles, moles and grams. You can do the same idea here. So let's say I have, we'll say 12.0 grams of NaCl. A question come up, hey, how many moles is that, Dr. Leslie? And we can do a conversion. We can use dimensional analysis. So 12.0 grams of NaCl. And what we know is its molar mass is there are 58.44 grams of NaCl per 1 mole of NaCl. And so if we do that conversion, 12 divided by 58.44, then our grams will cancel also, and we'll just be left with moles. And so this will give us that if we had 12 grams of sodium chloride, it is also true that we have 0.205 moles of sodium chloride. Now for now, that's just a thing we can calculate, right? We can calculate to grams to moles or moles to grams. In a following chapter, though, we will use this to then take that mole number and do more with. There'll also be something in this chapter when we get to a new type of unit, something called molarity, where we can use it as well. But in general, this calculation while it can be done on its own, is often a starting point where you'll then follow up with additional calculations. So there'll be more to go from there. But you can also do it by itself, and it's good to start with just a single step, and then we'll look at how you convert this into a multi-step part later on in this chapter and into the next one as well. So that's how you calculate molar masses and formula masses.